Okay, hi. Hi, am I audible? Aniket, can you hear me?
Yes, yes, you're audible. Yeah.
Okay, okay. And I assume my
Yes,
screen
yes,
is also
screen
visible.
yours.
Oh, thank you, sir. Okay, okay. So, hi, guys. Good evening. So, today we'll look at the uh, sort of a roundabout of what has been covered till week 10 of the oral course. So, since I'm actually traveling this week, so I don't have access to my tablet, so I won't be able to write anything in the classroom. But what I'll try to do is I have prepared a presentation sort of a material. So mostly I would be breezing through all of that has been covered in week 10 lecture content. And after that, if there is time, my plan is to basically maybe introduce you to another deep RL framework known as DDPG. So last week we looked at DQN. So this time we'll maybe have a look at DDPG algorithm. That's my plan. It's already 7:05. I think, yeah, we can start. Okay. So till now, what we have been looking at is the classical RL, which has been covered in the book of Sutton and Bartow, and the latest is a second edition book. But after week 9, what we are looking at is something more theoretical and more research oriented domain, and also this topic is not uh, covered in the RL textbook by Sutton and Bartow. So this field is known as hierarchical RL. So this field is being studied upon recently. I mean, not recently. It has been studied upon since a long time, but this has been important because there are several type of subtasks that a person needs to do or an agent needs to do in an RL setting before it achieves a final goal state. So let's say there are several other applications, be it in robotics and automation. So you want to maybe ask your agent to perform a variety of tasks, and at the end, the end goal is not the main intention, but the means uh, on which you acted upon to reach the goal. So the several learnings that are there in the along the path is also important to us. That afterwards, when I change the problem domain, so I don't have to start learning it, or I don't relearn everything again. So RL suffers from this problem known as catastrophic forgetting. Okay, so let's say I have learned how to eat with a spoon at my home. So if I go to a restaurant, so and I'm given a spoon, so it shouldn't be that I should have to optimize it all over again. I should learn how to eat with a spoon in a restaurant all over again. I should be able to take the learning that I have had in my home setting and be able to apply it to any generic setting, right? So this is the main intuition or main idea behind hierarchical RL. So the idea is that this helps in improving the performance. Uh, Second is the impossibility of RL to apply the impossibility to apply RL to problem with large state action pairs. So there's this so-called curse of dimensionality with increasing the size of the states or the action spaces. The problem becomes inherently difficult. So the number of state action pairs that one needs to look at when we are looking at different transitions, it becomes difficult to look at. So we resort to something like function approximation and so on. But even for further larger problems, then even function approximation fails after a certain point in time. That's why we need to have a look at some more of a hierarchy based learning. Second is that the sub goals and abstract actions can be used in different tasks. So the a given task can be separated or divided into small sub goals, or and each actions can be considered as some sort of abstract actions. So these sub goals can be learned separately and they can be used in a different setup. Second is that it allows for multiple levels of temporal abstraction. And third is that it enables us to get some sort of state abstraction. So by state abstraction, what we mean is that let's say you want to go from Let's say you want to achieve a big task, and in that big task, there are 4 or 5 different subtasks that you need to do in order to achieve the final state. So at every time instance, you need not have the idea or the access to the entire state space. So for achieving that particular sub goal, the only thing that is relevant to you is the states which are required to achieve that sub goal. So hierarchical RL also helps in giving us a framework for obtaining state abstraction. So I can give you an example. Okay, so if you look at my screen over here, so this is this problem known as the box world problem. Okay, it's an OpenAI Gym problem setup. So the box world problem is defined as such. So there is an agent. The agent has access to a certain colored key. The agent has to eventually find a gem. But to find the gem, the agent has to first open box number one. Inside box number one, there is another key. Then use that key to open another box. There is another key, and so on. And the game or the episode goes on until it reaches the final goal over here, right? So if you look at this GIF over here, so this white colored box is the gem. Okay, so the agent is represented by the gray color, yeah, and this is basically a lock and key pair. Okay, so this these are 2 pixels joined together. So there is a lock and there is a key. So on the right side is the lock. So if the same colored key matches with the lock, then the box opens. And inside the box, the content of the box is represented by the left pixel. Okay, so we'll just read through. Yeah, something like this. So this is the agent. The agent is represented by the gray pixel. This is a loose key. So the agent should learn to pick up the loose key. Then it should try to open up uh, the boxes which corresponds to the key that the agent has. So the boxes or the lock are the right pixels, right? So the agent can potentially open this, and this box. Okay. So if the agent opens this box, the agent gets the blue key, then from the blue key, the purple key, and then from the purple key, white key, and from the white key to the gem. So if the agent reaches here, the episode ends, right? But it can also happen that the agent can open a wrong colored box. So if the agent opens this part and it ends up with this, it's a potential dead end, right? Similarly, if it opens this box and gets this key, it's also a potential dead end. So you know you need to the agent needs to maneuver and plan accordingly to achieve this thing. So uh, this is one like place where using your typical RL algorithms like your Q learning or DQN would fail drastically, because this involves some inherent level of planning as well, right? So unless and until you have successfully decomposed your task into small subtasks, otherwise the training, the convergence would take really long time, unless and until the agent has explored each and every possibility at least 100,000 number of times. It won't be able to learn the correct behavior, right? So this is the general idea behind hierarchical RL. And by state abstraction, I mean, so let's say the agent has access to this, dark yellow key. So my state space, the complete state space would be the state space needed to reach the white gem. But now, since I have this yellow key with me, I only need to worry about what all boxes I can open and what all content lies inside it. I did not look at the bigger picture. So that way, I'm abstracting my state out by discarding all the, unnecessary or irrelevant information for that particular subtask. Okay, so this is the idea behind the state abstraction part. Second, professor talked about the different types of optimalities that one can find in the hierarchical RL setting. So first is the hierarchical optimality. So the hierarchical optimality is basically that the final policy is, the best policy with respect to the given hierarchy that is there in the problem statement. Then there is the recursive optimality. So in recursive optimality, the final policy is optimal with respect to the optimal policies learned by each of the subtasks. So basically, what I'm trying to do is the final policy is optimized. The final policy is This optimality is like defined by taking by aggregating all the optimal solutions for each of the given subtasks. And then there is a flat optimality. So the flat optimality is basically the expected optimal policy with the given environment. So irrespective of the hierarchy which is being followed or not, right? So these are the three types of optimality. So if you remember, Sir had given out this problem statement. So there is a bigger room. It has two doors, and it has to reach to the state G over here in this corner, right? So if I am trying to look at a hierarchical optimality, so all I need to do is in hierarchical optimalities, I need to first exit uh, room one, and I should go to room two, and then afterwards I need to go to the goal state G. So this is how the policy looks like in that case. Whereas this case is for the flat optimality. Okay, I think I said something wrong. Yeah, this case is sorry, this is for the recursive optimality, right? Because first I need to be optimal in exiting the room, and then I need to be optimal in reaching the goal. So if I've exited the room, reaching the goal is always go up, right? So this is basically the recursive optimality, and this is the hierarchical optimality. So I am optimal with respect to the hierarchy, and also in this case this hierarchical optimality is also equal to the equal to the flat optimality just in this case, but it can be very well be different if there might be some path which does not follow a hierarchy and can give uh, uh, a better policy, right? So turns out in most cases the flat optimality you know is gives a better policy in comparison to the hierarchical policy, which in turn gives better policy in comparison to the uh, recursive uh, recursive optimality. Okay, but there are also certain sub cases where a certain optimality is preferred over the other. So like in this case, you if it's an open map kind of a thing, so both this optimality kind of give similar results, but the hierarchical optimality uh, is preferred. But sometimes what happens is if there is some sort of an obstacle in between over here, okay, or some sort of a wall over here. So if the next subtask's goal is unknown, then chances are that that the recursive optimality might fail in that case, right? So yeah, and then next up, we take a look at the notion of a semi-Markov decision process. So in a Markov decision process, there is uh, chain or a sequence of state action transition that needs to be followed. So given you are in state ST, you pick action AT and go to a next state ST plus 1, getting a reward of RT plus 1. And so on, you carry on moving forward. Okay. So the semi Markov decision process makes a simple, relaxation or some sort of an assumption that the actions are not immediate, but they have some duration. So uh, it's like if you have taken that particular action, the action takes a certain time tau to get executed and to reach to the next state s of t plus tau, and this goes on ahead, right? So this tau can be thought of as the time taken for each decision to be executed. So one can think of it in a continuous fashion, that when I'm executing action a of t, it's like I know I have taken a decision, but I'll wait for certain time tau in order to execute the action and go to next state uh, st plus tau, right? So this sort of ensures some kind of continuity, so that it disregards the need for having any sort of intermediate states that the agent should be in while it is executing the action, right? So this is one way to look at it. So this is the basic idea behind the semi-Markov decision process. And if you were to define this, so It's again a four tuple. This consists of the state space, the action space, the transition probability, and the reward definition. So here the transition probability here instead of uh, like the next state being dependent on the current state and action, the next state and the time tau is also dependent on the current state and action that we are on the current state I am and the action that I'm executing. Okay, so this is in general supposed to be some sort of a joint distribution, but uh, from legacy terminology, people have been using the S prime and the tau in a decoupled fashion. So both of them correspond to different transition probabilities. And similarly, the reward function is basically the expected reward given the knowledge of S A S prime and also the tau, which is the time taken for the action A to be executed, right? And with this, you can also define the SMDPQ learning. So the SMDPQ learning is defined as it's similar to what Q learning was doing, but all we need to do is to change the definition of R of t, right? So in Q learning, we were taking R of t. So instead of R of t, we are taking R of t plus tau. So this R of t plus tau can in turn be, uh, rolled out and be written in terms of some sort of a discounted accumulating reward that you obtain over time tau after action A has been selected. So this can also be rolled out, and then this gamma tau. So this the discount factor is basically applied once with, and this is dependent on time. Uh, the time the agent took to execute that particular action. So this is how the SMDP Q learning looks like. So this is the general formulation for the SMDP Q learning, right? So so far we have discussed the need for hierarchical RL, the different types of optimality that hierarchical RL poses, and have given some sort of a context or introduction to semi-Markov decision process. Now, like I have 3 4 slides left. Maybe we can discuss in depth more about the two different types of framework that's discussed in week 10. Later on, he discusses another different framework, which we'll do it in the next class. So the first framework is known as the options framework. Okay. So options basically is a collection of actions that needs to be executed sequentially in order to achieve some sort of a higher macro action, right? So this macro action can be thought of as some sort of a high level action that needs to be done, whereas the low level action consists of the minute primitive actions that are taken in order to achieve the complete macro action. And the assumption is that there is an encapsulated policy. The policy of option pi o is given to us, and once the option is executed, we are constrained or bound to follow that particular policy. So an option, so the options framework, consists of three different things. First, in order to execute that option, I need to have, I need to satisfy the initiation set, right? So the initiation set can also be thought of as the preconditions that needs to be satisfied for that options to be executed. So this initiation set is defined by I naught, and these needs to be present in the start state itself. Then I need to have a policy pi of O, which maps from the states to the actions that I want to achieve. And then there is a set of terminating conditions, right? So if certain number of conditions are met, then you say that the action or uh, the option has been executed, and then I get basically a 0 1 kind of a variable which says that whether the termination condition has been met or not met, right? So think of it. I'll give you an example. You can think of it in terms of the taxi world domain. So let's say there is a taxi whose task is to pick up and drop passengers from a location A to location B, and there are 2 or 3 passengers in the grid world problem. So you need to first pick up passenger P1 and drop passenger P1 to location L1. After that, you need to pick up passenger P2 and drop passenger P2 at location L2, right? So there is some sort of a hierarchy that needs to be followed. So when you're trying to pick up passenger P1, what could be the initiation set, right? So the initiation set can be thought of, right? That the taxi should be present at location where the passenger P1 is present. So if that condition is met, then I tick that, okay, that is one initiation set. Second condition would be that the taxi should be empty. No other passenger should be sitting in the taxi at that particular moment, and that the taxi is, ready to be booked, so the passenger can hire or sit inside the taxi. So these could be, the two initiation set in the taxi world domain. There could be more if you think more closely, but I'm just giving a broad idea of what these preconditions needs to be. And then the policy is basically navigating through the grid world to reach location L1. And then the terminating condition is that the taxi is at location L1. The passenger has alighted from the taxi and has reached L2. Okay, so if these two conditions are met, then I said the option has been terminated. Okay, so the option is basically defined by this three. Uh, it's a three tuple which consists of the initiation set. There's a policy pi o, and there's a termination condition beta for each state, right? So now that we have defined the options framework, sorry, now we need to look at the different types of learning that is possible with the options framework. So first is the SMDP option queue learning. So in the last two, I think 2 slides back, I defined the SMDP queue learning framework. So when I have the options in the SMDP queue learning setup, all I need to do is replace the action that I have with the option, and the queue learning proceeds as follows, right? So this is the general idea behind the option queue learning. We'll look at how the updation also happens, right? And second thing is known as an intra-option queue learning. So in here, the updation happens for the option that you're following, or the option that you're executing. Sorry, you follow a pi and you execute an option. So the updation for state S happens when you're executing option O, but also the updation takes place when you're executing the primitive actions, constituting the options, right? So if an option consists of certain actions A1, A2 till A of n, so let's say this is the policy pi of O, and the trajectory is that there is S1, A1, S2, A2, and so on. So just neglect S1 for now, all the states right now. So you have a bunch of actions that needs to be executed in order to execute the option. So it so happens that I can, update the value of state S1. So this is the start state with all the primitive actions that are present in the options as well. So this is the basic idea behind intra-option queue learning. So you have all different primitive actions that is being used to update the queue value over here. This is similar to the normal queue learning setup. And this can also be and if you have defined this queue learning for queue of S1 A1, you can similarly define it for Q1 S1 A2, and so on. This is for the primitive update, and then for the final for the main option update. So this this can also be put here also. I mean, it's the option queue learning and the intra option queue learning. So the option update looks like this. So here, instead of taking max over this, I won't take, I remove the max because I am constrained by the policy pi of O, which is given to me. So an option consists of policy pi of O. I'm bound to follow that policy pi of O, right? So uh, unless the terminating condition is not met, I keep on following that particular option, and you know, uh, so I can't take sort of a max. So it's not like I can select the first action A and then thereafter select the best action. I have a certain you know set of actions that are fixed and that I'm bound to follow. So the max is missing in this part. But this is true if the next state S of 2 is not the terminal state. Okay. If the next state S of if S2 is terminal, then I can always bring back the max part because it's a terminal state. So this would hold true over here, right? So this is the basic idea behind the behind it, option queue learning, right? So there are two types. One is the SMDP option queue learning, which is this part, and then there is also intra option queue learning. Okay, so this is just a broad overview of what has been covered in the week so far, right? And then lastly, take a look at hierarchical abstract machines. This is another type of a framework. So this is different from the options framework. So what it does is it assumes, uh, using a finite state automata uh, in a hierarchical fashion, and we basically use that to uh, that is used to execute some hierarchical actions or some hierarchical or some tasks in a hierarchical fashion, right? So a hierarchical abstract machine consists of uh, four different states. First is the action state. So the action state is basically it corresponds to the primitive actions that needs to be executed. So when the action state is uh, is called or is uh, encountered, then when the action state is encountered, a certain primitive action is executed. Then there is a call state. So the call state basically passes on the control, right? So there are multiple different uh, hierarchical machines that are present pertaining to different subtasks. So the call state basically passes on the control from one particular from a parent MDP to some other MDP and so on. And then the choice state here basically sort of defines a non-deterministic transition in the finite state automata. So the choice state when like the choice state is encountered, I can non-deterministically make uh, I can non-deterministically make a transition to any of the to some other state, right? And then the stop state. So the stop state basically what it does is uh, it returns control to the you know up, upper upper automata or the upper machine, right? So the hierarchy is like the top is the parent MDP, and then from the call state you go down and down to the hierarchy. Once the stop state is encountered, the control is passed on back to the upper uh, machine over there, right? So this is the basic idea behind a hierarchical abstract machine. So this was one example that Sir had discussed in the class. So there is a certain grid over here. There's a certain grid world, and inside it there are small obstacles that needs to be avoided, and the obstacles are they are shaped like a stapler pin. So if you are stuck here, so there are two choices you can do. Uh, you can either follow the wall until you get out of the obstacle. Otherwise, you can simply back off and then select some random action and then proceed ahead. Right. So this is how the yeah. So this is how the hierarchical abstract machine looks like. So sorry. Yeah. Okay, fine. Yeah. So this is how this is the example problem that Sir had discussed in the class, and this is how the parent MDP sort of looks like. So it's like uh, I am always following a wall until and unless I reach some sort of an intersection. Sorry, I am always following a wall until I encountered an obstacle. Okay. If I encounter an obstacle, then I am in the choice state. Okay. So in the choice state, I can do two things. First is I can choose to follow the wall. So here I can follow the wall. Otherwise, I can back off and then take some other action and so on. So this follow wall and back up. So this follow wall and this back off. This keeps on going until some intersection point is reached, and once the intersection is reached, this is stopped, and the control is passed over to the upper uh, abstract machine and so on, right? So this is how the hierarchical machine setup looks like. So here the state space of the problem is basically h cross s, right? So h is basically the state of the underlying mdp, and s is the state space of the core of the parent mdp, right? So the actions are executed as usual. So you have, once the action calls, action states are encountered, the primitive actions are executed, which is adhering to the policies you know for which are defined on the states, right? And yeah, so when a call state is reached, the machine deterministically passes on control to the next in line, or the next uh, important abstract machine, and the process continues. So the learning here happens basically in the choice state. So the choice state is where the learning is happening. So the agent learns basically which machine to call next, or which action to execute. So this is where the entire learning is happening. So this is the general idea behind the hierarchical abstract machine, right? So uh, this is where the uh, entire learning is taking. This is a deterministic action. This is also deterministic action. This is a terminating condition. So this state basically defines the learning in this kind of setup. And also for doing this such kind of learning, you need to have uh, a proper uh, finite state automata designed to with all the proper hierarchy defined, right? So this is the general idea behind hierarchical abstract machines. So yeah, I think that's all I had with my slides for today. Uh, yeah, maybe I can take questions if there are any, or otherwise, as planned, I can move to explain something called deep deterministic policy gradient. So uh, last week I had uh, discussed in detail about DQN, right? So DQN is a uh, deep learning variant of the normal Q learning method. So we had seen how why deep learning is necessary, and how a Q learning problem can be transformed into a deep Q learning problem. Okay, so, but the only caveat there was that in a deep Q learning setup, the action spaces needs to be discrete, right? So the action spaces needs to be discrete, because that's how the Q learning is also defined, right? So it's max over A prime Q of S prime A prime, right? So this max is only defined if the actions are discrete, and this holds no meaning whenever we encounter a continuous action space, right? So this formulation, known as deep deterministic policy gradient, is can be thought of as DQN, but for continuous action spaces. Okay, so we'll take a look at what it is, right? So DDPG, or deep deterministic policy gradient, is an algorithm which concurrently learns a Q function and a policy. It uses off policy and Bellman equation to learn the Q function, and uses Q learning to learn the policy, similar to what was happening in DQN as well, right? So this approach is closely connected to Q learning and is motivated the same way. It's like if you know the optimal action value Q star, then the optimal action AS can be found by solving this, right? This is uh, uh, the Bellman optimality equation, right? So what DDPG does is it interleaves learning an approximator to Q star with learning an approximator to A star, and it does so in such a way which is specifically adapted for environments with continuous action spaces, right? So uh, DDPG. So policy. it involves, finding out the gradients and moving the policy in the direction of the positive gradient. So this deals with the policy gradient part. It's a deep learning algorithm because you involve neural networks for function approximation. So where does this deterministic part come in? So here the deterministic part comes uh, in the sense that the action that the neural network learns is some sort of a deterministic action. So there is no exploration which is happening, uh, but whatever it's done, it's a deterministic action. And the only way we can do an exploration is by adding some noise to the output of the neural network. Okay, so we'll look at that. Okay, so quick facts that is an off-policy algorithm, same as Q-learning. DDPG can only be used for environments with continuous action spaces. So DQN was for discrete action. Similarly, DDPG can only be used for continuous action space. DDPG can be thought of as deep Q learning for continuous action spaces. Spinning up implementation of DDPG does not support parallelization. Okay, so this website I'm referring to, this is known as spinning up AI, spinning up OpenAI. Okay, so if you visit this website, so this has a detailed documentation of different RL algorithms that are being used in current research as of today. There are proper documentation as well as good implementation of different algorithms. So I'm just referring here uh, to explain about DDPG today. Uh, yeah. So this is the Bellman optimality equation, right? Right. Uh, and this was the loss function in the DQN algorithm. So uh, this was basically the current estimate, and this is the bootstrap target that uh, we were trying to estimate, right? So in DQN, if you recollect correctly, this bootstrap target, since the same function approximator is used to estimate this target value and the current estimate. So this Q5 and Q5 are sort of similar. So I am in a way chasing a non-stationary target, right? So in order to uh, deal with that, so you basically make a copy of the target network, and freeze the weights. You are only updating the predicted network weight, and after some C number of iterations, you are copying the entire weights of the predicted network to the target network, right? So this was all that was there. And then there was the concept of replay buffer, right? So once you're encountering any state action state transition, you're storing it in a replay buffer. And once the replay buffer is full up to a certain limit, after that, you sample uniformly from it, and then you use it to update the weights based on the loss function, right? Uh, okay, so here in DDPG, so it's like calculating the max over targets in the action. So as mentioned, computing the maximum over actions in the target is a challenge in continuous action spaces, right? So DDPG deals with that using a target policy network to compute an action which approximately maximizes this Q of phi for the target policy, right? So there is a target policy network, there is a predicted policy network. So the target policy network, so you can understand it why I'm trying to only do this for the target policy network, because here uh, this max only comes in the target network. In the predicted network, I have no notion for a max, right? So earlier I was just copy pasting the policies from the predicted to the target. Now I need to, uh, actively tweak the target network to account for max over actions, right? Uh, okay. So the target network is found the same way as the target use function by Polyak averaging the policy parameters over the course of training. So putting it all together, Q-learning is DDPG performed by minimizing the following MSB loss with stochastic gradient descent, right? Uh, let's skip something. Yeah, yeah. Because the action space is continuous, the function q star is presumed to be differentiable with respect to the action argument. This allows us to set up an efficient gradient-based learning rule for a policy mu of s. So this mu of s is independent of the action. It's a deterministic action which exploits this fact. Then instead of running an expensive optimization subroutine each time we wish to compute this, we can approximate it with this thing. So basically, what you're doing is, yeah, earlier your neural network was in DQN. Your neural network was trying to, you know, uh, learn the corresponding, approximate the corresponding Q function for each individual actions because the actions were discrete, right? So now the input to the neural network is equal to the size of the state vector that you have. Then there are a bunch of hidden layers. And now the output is just a single neuron. Okay. And what that single neuron approximates, the single neuron approximates max of A over QS of A. So I am directly approximating this entire thing. I am approximating max of A Q of S comma A. So whatever the output that I am getting, which I'll call as mu of s, following policy mu. So this is directly doing max of a q of s comma a. So here this is a deterministic action that I'm taking, right? So that's why the name deep deterministic policy gradient. And whatever output that I get is some deterministic action given the state vector that I have given as input. And that's how the learning proceeds. Now since it's a deterministic action and uh, there is no implicit exploration which is happening in the target network, so in order to have some exploration, what you do is whatever uh, output you get from the neural network, you add some mean zero noise to it, right, in order to ensure exploration. So this noise that you add is an explicit noise that you are adding. Okay, it's not implicit in DDPG. So exploration is something which is explicit, right? So if exploration is not done, then more often than not, you will end up with a suboptimal policy. So this is something that needs to be taken care of. And yeah, I think mm, I think that's all I had. And then finally, there is this averaging which is happening, right? So uh, trick one was a replay buffer. All standard algorithms for training deep neural network make use of an experience replay buffer. This is a set of previous experiences. In order for the algorithm to have stable behavior, the replay buffer should be large to contain wide variety of experiences, but then it may not be good to keep everything. So if you use only the most recent data, you will overfit and things will break. If you use too much experience, you might slow down your training, right? So the way to look at it is, you sample uniformly batch wise after a certain point of time, so that you don't use the most recent experiences, and also you don't use all the experiences that are present in the replay buffer, right? So this is similar to the what you do in stochastic gradient descent, but the only thing is you're not doing a gradient descent, you are moving towards the direction of the gradient. So it's an upward ascent that you're doing, right? Second is the target network. So Q-learning makes use of target networks. So when we minimize the MSBE loss, we are trying to make Q-learning be more like the target. Problematically, the target depends on the same parameters we are trying to train. Phi. This makes the MSBE error unstable. The solution is used to use a set of parameters which comes close to phi, but with a time delay. That is to say, there is a second network called the target network, which lags the first. The parameters of the target are denoted by phi of tar. So in DQN-based algorithms, the target network is just copied over from the main network after every some fixed number of steps. In DDPG style algorithms, the target network is updated once per main network update by Polyak averaging. So this target network updates. So the phi is basically the theta or the weights corresponding to the target uh, to a neural network. So this phi of tar corresponds to the weights of the target network, and this is how the uh, uh, averaging happens. Okay, so this thing is known as Polyak averaging, right? So where rho is a hyperparameter between 0 and 1, usually close to 1. this hyperparameter is called polyac in our code, right? So this is how you're aggregating the target network and the uh, predicted network by means of polyac averaging. Okay, so this is the only difference. You do a polyac averaging, and instead of uh, approximating the q values for all the discrete actions, you are directly approximating the max over all the actions and then adding a noise to it, and then uh, performing updating the gradients, right? Everything is similar, only two three things are different. And turns out that this change enabled people to use the power of dqn for continuous action spaces, and uh, you know uh, like there are certain problems where DDPG outperforms many state of the art actor-critic methods and so on. But that is also very specific to the kind of problems or the type of games that you're subjecting the agent to, right? So this is the pseudo code for the algorithm for the deep deterministic policy gradient thing. So input policy parameters theta, Q function parameters phi, empty replay buffer D. Set the parameters target equal to the main parameters. This is the target uh, parameter for the policy. This is the Q function parameter. You observe state as select action A, and then okay, you also do some sort of a clip, right? Uh, you observe status and select action A according to clip of mu theta of S plus epsilon A low and A high. So what you're trying to do is uh, this is the max over all the Q max of A over Q of S comma A, right? This is mu theta of S plus some noise that you have added, and then this is bounded between some A low and A high, right? So this is always clipped. So if this value goes beyond A of high, you clip it and keep it at A high, and if it goes below A low, you clip it and keep it at A low. So this is some sort of clipping that you're doing. Then execute A in the environment, observe next state, reward, and done signal to indicate whether S is terminal. You store this thing in the replay buffer. If S is terminal, reset environment. If it's time to update, so if uh, the replay buffer is filled up to a certain limit, then for however many updates, you randomly sample batch of transitions from the replay buffer. You compute the target. This is the bootstrap target. Okay. Then you update the Q function by one step gradient descent. So basically, this is Q5 of S of A minus the target. You take the MSB loss, and then you do one step batch update, and then you update the policy by one step using gradient ascent. So this is the policy update which is happening. This is gradient ascent. And then finally, you update the networks by polyac averaging. So this is the phi which you are updating. This is the theta which you are updating. And you do this until convergence, right? Yeah. So I think this was all that I had for DDPG. If you have any questions, feel free to ask. Uh, Otherwise, I'm done from my end for today's lecture. Okay, I can stop sharing my screen. Okay, so I'm available for next 5 6 minutes. If you have any questions, you may ask. Otherwise, I'll wait till 8 o'clock. Okay. Okay, I think I've found one, uh, you know, tutorial for DDPG. Maybe I can, execute it, and maybe I can share it with you later. So since I have time, I can just try to run this code. Or I don't know. Maybe it will take some time. Okay. Meanwhile, I can explain what this environment here is about. So this is something known as a pendulum gym environment. So here it's an inverted pendulum setup. So the pendulum is fixed to uh, an axle. So it's pinned to a wall basically, and it can swing in clockwise on the anti-clockwise direction. So this is based on the classic problem in control theory. System consists of a pendulum attached at one end to a fixed point, and the other end being free. Pendulum starts in a random position, and the goal is to apply torque on the free end to swing it into an upright position with center of gravity right above the fixed point. So the pendulum is lying. The goal is to swing it so that it becomes upright after a certain time. So the diagram below specifies the coordinate systems used for the implementation. So XY Cartesian coordinates, and in meters, theta is the angle in radians, tau is the torque in Newton meter. Okay, so this is the action. Okay, so this is the action space. So the action space, it's a single action, uh, which gives me the torque. Min torque is -2, max torque is 2. The observation space is a vector of 3 elements. First element is the x, second is the y, which is the cos theta and sin theta. And the third element is the angular velocity. This is the min and max. The reward is defined as minus theta square plus 0.1. Then theta dt, which is theta dot square plus 0.0001 torque square. So this is minus theta square plus some point plus 0.1 times theta dot square plus 0.01 times torque square, right? So where theta is the pendulum's angle normalized between minus pi, zero being in the upright position. Okay. Based on the above equation, the minimum uh, reward that can be obtained is this value, while the maximum reward is zero. The starting state is a random angle between minus pi and pi, and a random angular velocity between -1 and 1. The episode truncates if the pendulum is in upright position or after 200 time steps. Yeah. So this is the gym environment. Uh, I don't know if it is okay. This is executed. I can run this. Run this. So here the replay buffer is behind. I'll just run this class. This OU noise. This OU process generates temporarily correlated exploration and effectively copes with physical control problems of inertia.
Hello,
Okay, so this is
Manav, hello.
yeah.
You're sharing your screen, huh?
Oh no. Wait.
I was thinking like, yeah, I.
Okay. I forgot.
Okay.
Okay. I'll restart them. So this is the pendulum environment problem, right? So there is a pendulum with a fixed point, and there is a free end. Okay. So the pendulum needs to swing, and it needs to come up in an upright position. So this is the action space. So action is basically the torque, which is between -2 and 2. The state space or the observation space is a vector of 3 elements. This is the x and the y coordinate, which is corresponding to cos theta and sin theta. And then there's the angular velocity. And this is the reward function, just minus theta square plus 0.1 theta dot square plus 0.001 torque square, right? So here theta is, normalized or wrapped between minus pi and plus pi. So theta 0 basically is the angle when it is in the upright position. So that's why minus theta square makes sense. So uh, since 0 is the case where we want to reach, so this makes sense. So for any other theta, I'm basically penalizing it. So it's a whole negative, right? So this is a penalty. Starting space is a random angle in minus pi and pi, and a random angular velocity in minus 1 comma 1. Uh, and yeah, uh, so this is a collab file that I found online, which has the implementation for DDPG. So this is for the pendulum environment. So I have executed these many these blocks till now. So this is where I'm importing all the modules. This is where I set the random seed. Uh, this is where the replay buffer class is defined. So this is executed. And this is the class for the OU noise. This is for adding a noise to the mu of S that is approximated by my neural network. So this class basically samples and adds some noise to the action that I'm doing. So this is the network. We are going to use two networks for actor and critic. Actor network has three fully connected layers and three non-linearity functions. ReLU for hidden layers and TANH for the output layer. On the other hand, the critic network has three fully connected layers, but is it used two activation functions for hidden plus input size of critic are sum of states and the action, right? Okay. So this is the network. So this is the summary for the DDPG agent class. So this class contains these many methods. So select action selects an action from the input space. Step takes in actions and return the response of the environment. Update model updates the model by gradient descent. Train is for training. Test is for testing. Target soft update is basically soft update from the local model to the target model. Okay, and so this is the C number of iterations over which the target update happens, and then plot is for plotting the training progress. So I've executed everything above. No. Okay. Okay. So this is the environment. And random seed. Okay. These are the initialization, the number of frames, memory size, batch size, and others. And okay, this is something which has already been trained. Uh, this was trained for 5,000 times frames. Maybe I can train it again for 10,000 frames. Let's see how much time it takes. Okay, not a lot of time it seems. Okay, I don't know why this did update, but okay, maybe for 50,000 times that. Turns out the learning here is not very stable compared to your standard actor critic method. Uh, so the variance is still there, but it's just sort of gives a method to approximate Q learning to the continuous space, but the variance still comes in because we are using sort of the same target parameters to update both the same policy parameters to update both the target and the current estimate, right? So that's why the variance is there, because we are still chasing a non-stationary target. So that part gets fixed when you look at your uh, traditional actor critic methods. When you separate it out, so there is an actor network, there's a critic network. One estimates the policy and the other evaluates the policy. So it's not by the same policy parameters, right? So this is done for 21,000 claims. Yeah, I think maybe it'll take a couple of minutes and we can run this and look at the render, how well it has learned. So you see, beyond a certain point, the actor loss, starts decreasing after a certain point in time. And then the critic loss, which was relatively stabler in the beginning, starts accumulating a lot of variance. Maybe because uh, here there is no cooldown of the epsilon, which is happening when we're doing the epsilon greedy thing. The epsilon is a constant and this is happening. So, this can also be a problem. So DDPG need not necessarily work well for all different kinds of problems, but you know, for some problem statement, it does give good results in comparison, right? So there's nobody left, right? Interesting. The actor loss has shot up earlier, but then it is decreasing each time. So variance is there, but is eventually giving good convergence, right? So this is for test. Let's go actively monitor it. How about trend? I don't know. Maybe I should take this. I'll just show what it has learned, whatever it was there. I'm not executing it right. Okay, so this is what it has learned after 50,000 episodes. So it learns to keep itself in this position, uh, like after some you know it basically has figured out a policy so that it makes a swing so that it eventually ends up in this position. Okay, so yeah, this was one implementation for DDPG. Think last week I had shown a similar implementation for DQN for the pendulum problem. So maybe this can be used, to compare uh, the performance aspect for both these problems. So the pendulum problem is a continuous action problem because I'm, the action is the torque which is between -2 and 2. And in the cardboard problem, the it was a discrete action where the action was either to go left or go right. Okay, so yeah, I think it's already 8:10. Maybe it's good time to wrap up the class. So thank you. I'll stop the recording and uh, have a nice weekend. Bye. Good night.